start off in the first unit of transformations and functions. Our first lesson, 1.1 in the textbook, is called horizontal and vertical transformations. A transformation from a mathematical perspective is an operation that is done to a graph and to a function so that it changes the shape of the graph and it changes the equation of the function in a very specific way. So a transformation can change the graph in its shape and its location, but often it keeps much of its characteristics. So if you're transforming a quadratic, often it will stay as a quadratic. The term mapping is often used to describe the change in points. So instead of saying transforming all the time, we might say the points are mapped into other points. So for example, the points of f of x are mapped into the image points of g of x. Image points simply mean the new transformed points. So let's take a visit back to grade 11 math. So grade 11 math, if y1 is equal to x squared, if you can recall, that is going to be this parabola right here, x squared, undergoes a transformation to become y2, x squared minus 2. Each point on y1 gets mapped into its image point on y2. Now, such that for this very specific transformation, the y's simply move down by 2. So our parent function y is equal to x squared starts off as a parabola right here. And as we transform it, we call this a vertical shift of 2, if you remember from last year. But essentially, all we're doing is, this is my new transformed graph, right? And I would say that this is going to be called y2. So that's y2. I hope that this makes sense. So this point notation is called mapping notation, and what we see here, we shifted the graph down by 2, so the y's value shifted by 2. So f of x is to denote a function. In transformations, in the language of transformations, f of x is often referred to as the parent or the initial fundamental function or graph that all transformations will be based upon. So if you recall from last year, if a parabola f of x is equal to x squared is transformed to become g of x, then f of x was shifted 2 units to the left and 3 units down. So since it was shifted 2 units to the left, h here is going to be -2. 3 units down, k is going to be -3. Now you may be wondering why that is. Recall from last year that the vertex form of a parabola is g of x is equal to a x minus h squared plus k. So that is the vertex form of the parabola, and as you did transformations last year, a changed the shape, h was the horizontal shift, k was the vertical shift. But you may recall though from last year, this x minus h really does change things. It is often the opposite of the transformation that you're expecting is the opposite of what you're expecting due to this form. So let's take a look at another example here. If the parabola f of x is equal to x squared is transformed to become g of x is equal to x squared minus 2 squared plus 3, then h was shifted 2 units to the right. So here h was going to be, 2 units to the right. Here we are. So h is 2. K is shifted 3 units up. So k is equal to 3. So h is 2, k is 3. I hope this sort of refreshes your memory. Let's get started on non-parabola transformations. Now remember, we're going to be talking about vertical translations, which simply is a shift up and down, and horizontal transformations, which simply is a shift left and right. All right, so let's get started here. Y is equal to, so we have two ways to write this transformation. It might take you a while to get used to this functional notation, but after a while it sort of becomes second nature. If y is equal to f of x plus k, this plus k, this constant, indicates that there will be a vertical transformation. If k is positive, we're going to be shifting it up k units. If k is negative, we're going to be shifting it down 2 units. So here, I'm going to start off and I'm going to write the mapping notation, and this is, I'm going to be writing in point notation. Let the black curve be the parent function that we wish to transform, right here. So we're going to transform that. I'm going to transform it up 2 units. So I'm just going to shift that up 2 units. So since I'm trying to shift it up 2 units, k is going to be equal to 2. So the equation of the graph, of the red graph, is y is equal to f of x plus 2. Now in functional notation, the red graph, well, we started off with a point xy, and this got transformed into point x, comma, y plus 2. Now let's go on to the blue. So the blue graph, it looks like, so if we take a look with the black one being our parent function, so I'm going to take this point. How did this point change? 1, 2. It moved 2 down. So the transformation on this is going to be y is equal to f of x minus 2. So now we have a point that we need to transform. So we had point x, y with the blue. How did those points change? Each and every point on the black changed to become the point of the blue by simply subtracting 2 from the y values. All right. So now we're going to deal with, so that's vertical shift. Vertical shift all has to do with the k, the constant. And this is what it looks like in functional notation. This is what it looks like in mapping notation. This is what it looks like for a specific example. Now, horizontal translations, somebody once said, it's always the opposite of what you think initially. Anyways, so let's move a graph horizontally. So horizontal translation, if h is greater than 0, then the graph is shifted to the right. Now that might make sense because on the Cartesian plane, the x is positive in the right direction. So if h is left or less than 0, negative in other words, then the graph is shifted h units left. Now look how it appears in functional notation here. So allow me to switch colors, and I'm going to start talking about the red again. So the red. So the black is my parent function. If I chose to transform it to become the red function, it would look very similar like this. So I would get y is equal to f x minus 2. I did not make a mistake there. I know I didn't. It's odd, I agree. I'm moving it to the right, 1, 2. Generally, the h is positive here, and I'm going to argue that h is positive when I write x minus 2. If you draw your attention to here, it's because of the way it's written in this form. Each point, if I'm going to transform it, so on my original function, y is equal, or x, sorry, I'm talking about a point now. Point xy we change into point x plus 2 because it's to the right, and the y remains unchanged. I hope that helps. Now allow me to talk about the blue function. Now the blue function here, it looks like h is going to be negative 2 here because we're moving it to the left. If we move it to the left, h is negative 2. I promise I am not making a mistake. So if I write my functional notation, it appears as x plus 2. Weird. And my point notation changes in the way so since it was left, you need to subtract 2 from your previous x values. So perhaps, maybe I should explain this once more. This is your first x, y values, and then these are your image points of your new graph.